For as long as we've looked into space, there was one chapter we thought we understood. The beginning, a dark, empty universe. No stars, no galaxies. Just a slow, quiet build-up toward the first light. Simple, predictable, safe. But then the James Webb Space Telescope looked deeper than anything before it and found something it wasn't supposed to. Not faint, not primitive, not early in the way we expected. It found something bright, something massive, something that looked finished in a time when the universe itself was barely beginning. And that's the problem. Because according to everything we thought we knew, structures like this shouldn't exist yet. There simply hasn't been enough time. Not for stars to form, not for galaxies to evolve, and definitely not for complex chemistry to emerge, but it's there. Which means one of two things is true. Either this object is breaking the rules, or the rules themselves are wrong. Right now, astronomers are being forced to reconsider one of the most fundamental stories ever told, the origin of everything. So what exactly did we find, and why is it shaking our understanding of the cosmos? To answer that, we need to go back, before stars, before galaxies, to the very first moments after the Big Bang. Because the deeper you go into that beginning, the less certain it becomes. There is something quietly beautiful about the fact that we can even ask this question. That a species that didn't exist 100,000 years ago, on a small rocky world, orbiting an ordinary star somewhere in the middle of a fairly unremarkable galaxy, it has built a machine capable of looking back 13.5 billion years and asking what was there. Not imagining it, not guessing it, actually seeing the light that traveled across almost the entire age of the universe to reach a mirror floating silently in the cold of deep space. That machine is the James Webb Space Telescope, and what it has been finding, quietly, methodically, image by image, has been rewriting the oldest story ever told. Not loudly, not with fanfare, but with the kind of slow, gentle certainty that comes from simply looking more clearly than anyone has ever looked before, and seeing things that were never supposed to be there. This is that story. To understand what James Webb found, and why it matters so much, you have to understand what we thought the universe looked like when it was very, very young. Now, not young in the way a child is young, or even in the way a civilization is young. Young in the way that makes all of human history feel like the last breath of a very long exhale. The universe is roughly 13.8 billion years old. To put that in terms that might actually land somewhere in your mind, consider this. If you compress the entire history of the universe into a single calendar year, our entire solar system, the sun, the earth, every ocean and mountain and creature that has ever lived here, doesn't form until September. Modern humans don't appear until around 11:59 on the night of December 31st. And all of recorded human history, every empire and civilization and scientific discovery, every book ever written and every song ever sung, takes place in the last 10 seconds of that year. And the universe was doing things for an incomprehensibly long time before we existed to notice. And in the very beginning of that year, in the first fractions of the first second of January 1st, something extraordinary happened. Everything that exists, all the matter and energy and space and time that makes up the cosmos, emerged from a single point of unimaginable density and temperature. We call it the Big Bang, though that name is a little misleading. It wasn't really an explosion in the way we imagine explosions. There was no empty space for something to explode into. Space itself began to expand. Matter and energy were born together, inseparable, yet in a state so hot and so dense that the familiar rules of physics we know, the rules that hold atoms together and keep planets in orbit and allow stars to burn, those rules didn't quite work yet. The universe in those first moments was something we don't have a word for. It was a kind of cosmic infancy so extreme that the concepts we used to describe reality hadn't fully crystallized yet. In the first few minutes, the universe cooled enough for the simplest atomic nuclei to form. Hydrogen, helium, a trace of lithium. That was it. The entire periodic table of elements. All the carbon and oxygen and iron and gold and every other atom that makes up everything we see. None of that existed yet. Just three elements, the simplest ones, born in the first moments of time. And then something happened that doesn't get talked about nearly enough. Something that set the stage for everything that followed, including what James Webb eventually found. The universe went dark, not the kind of dark you experience on a cloudy night. Not even the dark of deep space as we know it today, dotted with galaxies and glowing with distant light. This was a different kind of dark, a fundamental, absolute darkness that lasted for hundreds of millions of years. Astronomers call it the cosmic dark ages, and it's one of the most haunting chapters in the history of everything that has ever existed. Here's how it happened. After the first few minutes, the universe had its hydrogen and helium, but these atoms weren't yet fully formed. The electrons that belong on the outside of atoms were still too energetic, still moving too fast, and still too hot to settle into stable orbits around the nuclei at the center. So the early universe was filled with a kind of hot plasma, a fog of charged particles so dense that light couldn't travel through it. Photons, the particles that carry light, would travel for only a short distance before crashing into a free electron and being scattered in a new direction. The universe was opaque. Light existed, but it couldn't go anywhere. Everything was trapped inside a glowing, featureless fog. Then, about 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons could finally slow down enough to be captured by the hydrogen and helium nuclei, in what cosmologists call recombination, though that's slightly misleading since the electrons had never been combined before. Atoms formed for the first time, and the moment those electrons settled into place, the fog lifted. The universe became transparent. The light that had been trapped suddenly had nowhere to crash into. It flooded outward in every direction. That ancient flash of light is still traveling through the universe today. We can detect it. We call it the cosmic microwave background radiation, and it's the oldest light we can see, a kind of afterglow from that moment when the universe first became see-through. But here's the haunting part. Once that initial flash of light spread out and thinned across the expanding universe, there was no more light coming from anywhere. Stars didn't exist yet. Galaxies didn't exist yet. Yet the universe was filled with hydrogen and helium gas, slowly cooling, slowly drifting, slowly being pulled together by gravity into slightly denser clumps. But those clumps weren't dense enough to ignite. They weren't hot enough at their centers to trigger nuclear fusion. There were no thermonuclear fires burning anywhere in the cosmos. No light of any kind. Just cold gas in absolute darkness. For hundreds of millions of years. The universe sat in that darkness, patient and quiet, while gravity did its slow and silent work. This period, from about 380,000 years after the Big Bang until the first stars finally ignited, somewhere between 100 million and several hundred million years later, is what we call the cosmic dark ages. And it's not just poetic to call them that, it's literally accurate. The universe was dark. There was nothing to see. If you had somehow been there, you would have been floating in an absolute blackness broken only by the very faint, very long wavelength glow of the cosmic background radiation, invisible to human eyes. The universe was a quiet, dark, cooling sea of gas. And somewhere in that sea, the seeds of everything that would eventually exist were quietly taking shape. The end of the Dark Ages, the moment when the first stars finally lit up, is one of the most dramatic events in cosmic history. We call it the Epoch of Ionization. It's one of the least understood and most scientifically important periods in the history of the universe. And it's precisely the period that the James Webb Space Telescope was built, more than any other reason to explore. One, because the Epoch of Ionization is where everything changed. It's where the universe went from being a cold, dark, featureless sea of gas to the luminous, complex, galaxy-filled cosmos we see around us today. And the objects that James Webb has been finding from this era, the first light, the first structures, the impossible galaxies at the edge of cosmic time, are rewriting our understanding of how that transformation happened. Because the story we thought we knew, the simple, orderly story of gas slowly gathering into stars that slowly gathered into galaxies, turns out to be wrong in ways that we are only now beginning to understand. Before we get to what James Webb found, it's worth taking a moment to appreciate just how hard it is to see anything from this period at all. When light travels fast, about 186,000 miles every second, nothing we know of travels faster. But the universe is so large that even at that speed, light takes billions of years to cross it. When you look at a distant galaxy through a telescope, you're not seeing it as it is now. You're seeing it as it was when the light you're detecting left it. The farther away the galaxy, the further back in time you're seeing. A galaxy that's 1 billion light years away appears to us as it was 1 billion years ago. A galaxy 10 billion light years away appears as it was 10 billion years ago. The telescope is a time machine, and the further back you look, the younger the universe you're seeing. The problem is that the most distant galaxies, the ones from the earliest time, the ones just emerging from the dark ages, are also the faintest. They're far away, which means their light has spread out over enormous distances. They're young, which means they haven't had time to build up the massive star populations that make nearby galaxies so bright. And there's another problem. The expansion of the universe stretches the light as it travels. Light that was originally emitted in ultraviolet wavelengths, the shortest and most energetic wavelengths of visible light, gets stretched by the expansion of space during its long journey. By the time it reaches us, it may have been stretched all the way into the infrared, wavelengths much longer than visible light, invisible to human eyes and to telescopes like the Hubble Space Telescope that were designed primarily to see invisible wavelengths. And this is exactly why James Webb was designed the way it was. It operates primarily in infrared light. Its mirror, that iconic gold hexagonal structure, is 6.5 meters across, nearly 3 times the size of Hubble's mirror. It sits at a point in space called L2, about 1 million miles from Earth in the direction away from the Sun, where it can keep its instruments permanently shielded from the heat of the Sun and Earth and Moon, allowing them to cool down to temperatures where they can detect the extremely faint infrared signals from the earliest galaxies. It took decades to design, nearly 30 years to build, about $10 billion to complete, and it was launched on Christmas Day 2021 on a rocket that delivered it perfectly to its destination. And when it opened its golden eye on the universe, it began to see things that no one had ever seen before. The first hints that something unexpected was happening came quickly. Scientists had expected James Webb to push the frontier of the observable universe back a little further than Hubble had managed. They expected to find a few very distant, very faint, very primitive-looking galaxies from the earliest cosmic times. What they found instead was something that stopped the field in its tracks. Not a few faint smudges. Not primitive, undeveloped blobs of gas and dust. The telescope found galaxies that were massive, bright, chemically complex, in some cases, already finished forming stars, in a period of cosmic history when none of that should have been possible. Let's slow down here and sit with that for a moment, Nash, because it's worth really understanding why these discoveries are so startling. The standard model of cosmology, the framework that describes how the universe grew from the Big Bang into the structure we see today, makes very specific predictions about what galaxies should look like at different epochs. In the earliest times, shortly after the Dark Ages ended, the model predicts that galaxies should be small. They should be primitive. They should be actively forming their first stars. They should contain mostly hydrogen and helium, because those are the only elements that existed at that point. The heavier elements, oxygen, carbon, iron, everything else, have to be forged inside stars and scattered into space. When those stars die in supernova explosions, that takes time, many generations of stars living and dying. Yet the model predicts that the very first galaxies in the very earliest times should look like the raw material of what would eventually become the galaxies we see today. Not finished, not evolved, just beginning. What James Webb found was something that didn't fit that picture. at distances corresponding to when the universe was only a few 100 million years old, well within the period we'd expect to see only primitive, just-hatching galaxies. The telescope found objects that looked far more developed than they had any right to be. Some of them were more massive than the Milky Way in total stellar mass, despite existing when the universe was only a tiny fraction of its current age. And some of them were already showing signs of chemical enrichment, the presence of oxygen and other heavy elements that should have required many generations of stars to produce. Some of them appeared to have already gone through a rapid burst of star formation and then quieted down, what astronomers call quenching, a process that in the modern universe takes billions of years to complete. These galaxies had apparently done it in a few 100 million years. The universe, in other words, had grown up extraordinarily fast. The discovery that put this most starkly into focus came in May 2025, when a team at Yale University announced the detection of a galaxy they named Z14, short for Mother of Miracles. The light from this galaxy left its source when the universe was only 280 million years old. It had been traveling toward us for 13.5 billion years, before the James Webb Space Telescope intercepted it and decoded it into an image. And what that image showed was a galaxy that was bright, shockingly bright, despite being from such an early time. It was tiny in physical size, only about 500 light-years across compared to the 100,000 light-years that span the Milky Way today. But from that compact little structure, it was blazing with the light of millions of stars forming at a furious rate. The team's lead researcher, Peter Van Dokkum, gave an interview after the announcement and reached for a comparison to make the timescales feel real. He pointed out that sharks have been swimming in Earth's oceans for longer than the age of this galaxy was at the time its light was emitted. As the ocean predators that predate every major mass extinction in Earth's history, creatures that were already ancient when the dinosaurs first appeared, represent a longer stretch of continuous existence than the entire age of Z14 when it was observed. That comparison should sit with you for a moment. Something so old it outlasted the dinosaurs is younger, by a significant margin, than the universe was when this galaxy's light began its journey toward us. And Van Dokkum added something else. He said that James Webb was not supposed to discover any galaxies this early in the universe's history, not at this point in the mission, not from the very first years of operation. Yet the discovery pipeline had been designed with expectations built around the idea that galaxies this distant would be extraordinarily rare, if they existed at all as bright, detectable objects. Those expectations have been shattered, one after another, with almost every new data release. By early 2026, more than 100 galaxies similar to Z14 had been cataloged from just the first 400 million years after the Big Bang. The number grows with every new pass through the data. Astronomers expected a handful of faint, primitive smudges from this era. They are finding something that looks increasingly like a crowd. A very ancient, very unexpected, very bright crowd that has no obvious place in the story we thought we knew. To understand why this is so troubling for the standard model, you have to understand a little bit about how astronomers think galaxies are supposed to form. The story goes something like this. In the beginning, after the Big Bang, the universe was almost perfectly uniform. Almost, but not quite. There were tiny variations in density. Some regions were ever so slightly denser than others, by amounts so small they'd be almost undetectable even with the most sensitive instruments we have. But gravity doesn't care how small a difference is. Over time, the denser regions pulled in more matter from their surroundings. They got denser. That made them pull more matter. The process was slow at first, agonizingly slow, but gravity is patient and it has billions of years to work with. The first structures to form were not galaxies. They were something even more fundamental, clumps of dark matter. Dark matter is one of the great mysteries of modern physics. We can't see it. It doesn't emit or absorb light. We know it exists only because of its gravitational effects on things we can see. Galaxies move in ways that only make sense if there's far more mass present than the visible stars and gas can account for. Dark matter makes up about 27% of the total energy content of the universe, compared to only about 5% for the ordinary matter that makes up stars, planets, people, and everything else we can directly detect. It forms invisible halos and filaments, a vast cosmic web of invisible scaffolding. And it was this dark matter web that first organized itself into structure after the Big Bang. As dark matter clumps formed and grew, ordinary matter, hydrogen and helium gas, followed. It fell into the gravitational wells carved out by the dark matter halos, pooling and concentrating in their centers. As the gas concentrated, it heated up. As it heated up, it began to radiate energy away. As it radiated energy, it cooled and contracted further. Eventually, in the densest regions, the gas became so concentrated, so compressed, that temperatures and pressures at the center reached the threshold required for nuclear fusion to ignite. Hydrogen atoms began slamming together hard enough to fuse into helium, releasing enormous amounts of energy in the process. A star was born, and then another, and then billions more. The Dark Ages ended. The universe lit up. This story, dark matter halos forming first, gas falling in, stars forming within the gas clouds, and those stars gathering into the first primitive galaxies, is the foundation of the standard model of galaxy formation. It has been extremely successful. It explains a huge amount of what we observe in the universe today. The large-scale structure of the cosmos, the way galaxies cluster and filament and avoid the great voids between them. All of this follows naturally from the physics of dark matter halos growing and merging over cosmic time. The model predicts that galaxies should grow over time, starting small and primitive and gradually building up mass and complexity through star formation and mergers. It's a coherent, well-tested, widely accepted framework. And James Webb keeps finding things it didn't predict. The fundamental problem isn't just that the early galaxies are bigger than expected, though they are. It isn't just that they're brighter than expected, though they are. The deepest problem is one of timing. Building a galaxy as massive and complex as some of the ones James Webb has found in the first few 100 million years after the Big Bang requires an almost unimaginable rate of star formation. Astronomers measure star formation in units of solar masses per year. How many suns worth of new stars a galaxy is creating each year. The Milky Way today forms stars at a rate of about 1 to 3 solar masses per year. It's a mature, relatively settled galaxy. Some of the galaxies James Webb has found in the very early universe appear to have been forming stars at rates of hundreds to thousands of solar masses per year, sustained over periods of tens of millions of years to build up the stellar masses they show. Those numbers strain every model of how star formation is supposed to work. In today's universe, star formation is a self-limiting process. When massive stars form, they're extraordinarily energetic. They blast out ultraviolet radiation that ionizes the surrounding gas, making it too hot and too diffuse to collapse into more stars. When those massive stars die, and they die young, after only a few million years of burning, they explode as supernovae, sending shockwaves through the surrounding gas that heat it up and push it away, further suppressing further star formation. This feedback process keeps the overall efficiency of star formation relatively low. In any given cloud of gas, only a small fraction, typically a few percent, will actually end up in stars. And the rest gets heated and dispersed by the energy from the stars that do form. In those first galaxies, those first few 100 million years after the Big Bang, the standard model suggests that this feedback process was already operating. Stars would form, generate energy, and that energy would limit how quickly more stars could form. The result should be a galaxy that grows relatively slowly, constrained by its own stellar activity. But the galaxies James Webb is finding in the very early universe appear to have formed stars at efficiencies that are far beyond what any known physical process can produce. Some calculations suggest efficiencies of 50% or higher, meaning half of all the available gas was converted into stars. In today's universe, that number is typically 1 to 5%. Even under the most favorable conditions the standard model can imagine, theoretical maximum efficiencies top out at 10 to 20%. 50% has no mechanism. 100%, which some of the most extreme early galaxies seem to require, appears physically impossible under the physics we understand. This is not a minor discrepancy. This isn't the kind of thing that gets resolved by adjusting a parameter in a simulation, or by discovering that a systematic error in the data has been inflating the apparent brightness of these galaxies. Researchers have been careful. They've applied multiple cross-checks. They've verified the distances with spectroscopic measurements, not just photometric estimates, but direct measurements of specific atomic emission lines at known wavelengths that provide unambiguous distances. The galaxies are where the data says they are. They are as bright as the data says they are. And their brightness, at those distances, in those early times, requires explanations that our current models don't contain. Several possibilities have been proposed. One of the most interesting involves the nature of the very first stars. The first generation of stars, forming from pure hydrogen and helium, with no heavy elements at all, would have behaved very differently from stars that form today. Without the heavy elements that help gas clouds cool efficiently, those first stars are thought to have been very massive. Some models suggest hundreds of times the mass of our Sun, far larger than anything that forms in the modern universe. More massive stars burn hotter and brighter. They produce more ultraviolet light per unit of mass. And they live faster and die sooner, but while they shine hard. If the early universe was dominated by these enormous first-generation stars, it would have been intrinsically much brighter per unit of stellar mass than the models based on modern stellar populations assume. James Webb might be detecting a universe that was simply more luminous than expected, not because there's more mass than expected, but because the stars themselves were a different, more extreme kind of star. Another possibility involves the feedback process itself. In today's universe, the energetic feedback from massive stars, the radiation and supernova shockwaves, is very effective at limiting star formation. But the conditions in the very early universe might have been different in ways that reduced the effectiveness of this feedback. The gas in those first galaxies was simpler. Fewer heavy elements means different cooling and heating behavior. The geometry of those first systems might have been different, more compact, more chaotic, with gas flowing in from cosmic filaments at rates that overwhelm the feedback. Some models suggest there might have been a brief window in the very early universe when star formation could proceed in a kind of feedback-free mode, forming stars at efficiencies far higher than anything seen today, before the first supernovae had time to heat and disperse the surrounding gas. If that window existed and was as productive as some models suggest, it could explain some of what James Webb is seeing. A third possibility, and this one is particularly interesting, involves the role of supermassive black holes. At the center of essentially every large galaxy we know of, including our own Milky Way, there sits a supermassive black hole, an object millions or billions of times more massive than the Sun. So dense that not even light can escape its gravitational pull once it crosses the event horizon. In some galaxies, these central black holes are actively consuming surrounding gas, and as that gas spirals in toward the black hole, it heats up and releases enormous amounts of energy, often more energy than all the stars in the galaxy combined. These are what we call quasars, or active galactic nuclei, and they are among the brightest objects in the universe. If some of the early galaxies James Webb is detecting harbor active central black holes that are contributing significantly to their brightness, then their apparent stellar masses might be overestimates. Part of that luminosity is coming from the black hole, not from stars. This doesn't resolve the mystery entirely, because even accounting for active black holes, many of the early galaxies still seem more massive and more chemically evolved than they should be. But it softens the problem somewhat. And then there's the oxygen. This might be the single most startling discovery that came out of the first years of James Webb observations. In early 2025, 2 independent research teams published results simultaneously, and having worked from the same data through completely separate methods, showing that a galaxy from when the universe was only 290 million years old contained 10 times more oxygen than any reasonable model predicted it could have produced in the short time it had existed. 2 independent teams. The same result, working separately. That kind of independent confirmation makes a finding essentially impossible to dismiss. To understand why oxygen is so extraordinary at this distance, you have to understand where oxygen comes from. The Big Bang produced hydrogen and helium almost exclusively. Every atom of oxygen in your body, in Earth's oceans, in the air you breathe right now, was forged inside a star that lived and died before our solar system formed. Oxygen is made through nuclear fusion in the cores of massive stars. And when a massive star exhausts its fuel and explodes as a supernova, it scatters all that freshly forged oxygen into the surrounding space. The next generation of stars and planets forms from that enriched material, inheriting the oxygen from all the stars that came before. But that process takes time. Stars must form. They must burn through their fuel, which takes at least a few million years even for the most massive, fastest burning ones. Then they must die, explode, and scatter their contents. Then the debris must cool and be incorporated into the next generation of star-forming clouds. Then those clouds must collapse. Those stars must burn, and those stars must die before the next layer of chemical enrichment can occur. And for a galaxy to show 10 times more oxygen than expected, when the universe was only 290 million years old, multiple complete cycles of stellar birth, burning, and violent death had to have already occurred inside it. Multiple generations of massive stars, each generation enriching the raw material available to the next, living and dying at an extraordinary rate in an extraordinarily short time. One of the researchers who found this described it as finding an adolescent where you would only expect babies. The galaxy was chemically mature in an infant universe. And the word mature here isn't figurative. The oxygen abundance they measured is a direct chemical fingerprint of how many generations of stellar evolution the galaxy had already experienced. That fingerprint said many. Far more than should have been possible. This discovery connects directly to the story of what the James Webb Space Telescope was looking at when it found these objects from beyond the Dark Ages. Because the first object beyond the Dark Ages isn't just a single galaxy discovered on a single day. It's a category of discovery. A growing catalog of objects from the earliest cosmic epoch, each one pushing the boundary of what our understanding of the universe can contain. And each one adding a new piece to a puzzle that is becoming increasingly difficult to ignore. Let's talk about what the Dark Ages actually looked like from the inside, because it's worth dwelling on just how strange and quiet those hundreds of millions of years were. Imagine you could somehow be present in the universe during that period. You'd be floating in something that looks, to human eyes, like perfect blackness. The cosmic microwave background radiation, the afterglow of the Big Bang, would be all around you. But by this time it would have cooled and stretched to microwave wavelengths, completely invisible to any detector built from ordinary matter. There would be no stars, no planets, no sources of electromagnetic radiation at any wavelength that would register as light in any familiar sense. Just hydrogen and helium gas, the faintest possible structure beginning to take shape under gravity's patient guidance. And silence. Not just absence of sound, space is always silent, but absence of the kind of electromagnetic energy that we associate with activity, warmth, life, light of any kind. Yet the universe during the Dark Ages was anything but static. Yes, gravity never stopped working. From the moment of recombination, when atoms first formed and the universe went transparent, dark matter halos had been slowly growing, pulling in more and more mass, deepening their gravitational wells. The hydrogen and helium gas followed, falling into those wells and gradually concentrating at their centers. The universe was building the scaffolding for everything that was going to come next, doing it silently and invisibly over hundreds of millions of years. Like the scaffolding going up around a building before the construction crews arrive. You can't see what the building is going to look like yet, but all the support structures are already in place. The end of the Dark Ages was not a single clean moment. Different regions of the universe lit up at different times. At the first stars to ignite were almost certainly in the densest regions, the places where dark matter had concentrated most efficiently and where the gas had pooled most deeply. These first stars may have been the most extreme objects that have ever existed, objects so massive and so hot and so bright that they would be essentially unrecognizable to anyone familiar only with the stars we see today. Some models suggest the very first generation of stars, what astronomers call population 3 stars, may have been hundreds of times more massive than our Sun, burning at temperatures that dwarf anything in the modern stellar population, living for only a few million years before exploding in supernovae so powerful that the explosions themselves would have been visible, in principle, across enormous distances. Those first stellar deaths seeded the surrounding gas with the first heavy elements, and the story of the universe after the Dark Ages is, in large part, the story of how that chemical enrichment propagated outward, generation after generation, cycle after cycle, slowly building up the complex chemistry that would eventually give rise to rocky planets, liquid water, organic molecules, and eventually, after billions of years, organisms capable of looking back across that entire history and asking what happened. But the discoveries from James Webb are suggesting that this story, the gradual generation by generation buildup of chemical complexity, happened faster than we thought, much faster, unsettlingly faster. And this connects to what may be the deepest and most philosophically interesting implication of everything James Webb has been finding. Because if the universe built up complexity faster than our models predict, if the first galaxies were bigger, brighter, and more chemically evolved than they should have been, then either the physics of galaxy formation in the early universe was fundamentally different from what we think, or our understanding of the underlying cosmological framework itself needs revision. And either of those possibilities is significant, not because it means the standard model is wrong. Decades of extraordinarily precise observations have established the core framework of modern cosmology on very solid ground, but because it means there's something we're missing. There's something that was operating in the early universe that we haven't correctly captured in our models, and finding out what that something is might change our understanding of the universe in ways we can't fully anticipate yet. One of the most intriguing discoveries from James Webb's early operations came not from a survey of many galaxies, but from an extremely long, extremely deep look at a single target. A gravitational lensing cluster called Pandora's Box, formerly known as Able 2744, is one of the most powerful natural magnifying glasses in the observable universe. It's a collision between multiple massive galaxy clusters, all slamming together in slow motion, slow relative to a human timescale, but at millions of miles per hour on any cosmic scale, creating an object of almost unimaginable mass concentrated in a relatively small region of sky. That mass bends the paths of light passing through it, just as a glass lens bends the path of light passing through it, but on a scale that no piece of glass could ever match. Through this cosmic lens, James Webb was able to peer at objects so distant and so faint that without the amplification they would be completely invisible to any telescope ever built. What the telescope found through Pandora's Box included some of the most distant individual galaxies ever detected, some of them from within the first 100 million years of cosmic history, uncomfortably deep into the Dark Ages, in a period where our models suggest there should be almost nothing to see. Yes, and among those objects were things that genuinely surprised the research teams who found them. Small, compact, extraordinarily dense clusters of stars, objects that appear to be the ancestors of the ancient globular clusters we see orbiting our own Milky Way today, formed when the universe was only a few 100 million years old, packed with stellar densities thousands of times higher than anything we see forming in galaxies today. 5 of these objects were found in a single lensed galaxy at a redshift of approximately 10, meaning we're seeing it as it was when the universe was only about 460 million years old. They were named the Cosmic Gems Arc, and what makes them so extraordinary is not just their age, but their density. And the stellar surface densities inside these 5 compact clusters are roughly 1,000 times higher than the densest young star clusters observed anywhere in the nearby universe. At those densities, something interesting and potentially very important happens. When stars are packed that tightly together, they interact gravitationally on timescales shorter than their individual lifetimes. Runaway stellar mergers become possible. Star after star falling into a growing central mass, accumulating until you have an object so massive it can't have formed through ordinary stellar evolution. One of the proposed pathways for this process leads to the creation of intermediate mass black holes, objects in the mass range between stellar black holes, which form from individual supernovae, and in the supermassive black holes found at the centers of galaxies. These intermediate mass black holes have been theorized for decades. They've been difficult to find and confirm. The cosmic gems clusters may be showing us exactly how they form, in the densest, earliest star clusters at the beginning of cosmic time. There's something quietly profound about this. The globular clusters that orbit our Milky Way today, those ancient spherical balls of hundreds of thousands of stars, glittering like tiny jewels scattered around our galaxy, are relics. They are, most astronomers now believe, the survivors of a process that happened when the universe was very young. They are the remnants of the very first dense star clusters that formed in the very first galaxies. We've been able to see them in the nearby universe. And we've known they were old, but now James Webb is showing us what they looked like when they were young, when they were forming, in the first few 100 million years of cosmic history. It's like finding a photograph of your grandparents as children, the same entity, just at a vastly different stage of its life. And what those young clusters looked like was something far more extreme, far more packed with energy and activity than the quiet, ancient stellar communities they eventually became. The question of how light from these early objects reaches us at all is worth sitting with, because it connects directly to one of the most remarkable things about modern astronomy, the way the universe itself has cooperated with our desire to see it. Gravitational lensing, the bending of light by massive objects along the line of sight, as is predicted by Einstein's general theory of relativity. Einstein published that theory in 1915. The first observational confirmation came in 1919, during a solar eclipse, when Arthur Eddington measured the slight deflection of starlight passing close to the edge of the sun, exactly the deflection Einstein's equations predicted. Einstein's theory has been tested thousands of times since then, in contexts ranging from GPS satellites to the merger of neutron stars, and it has passed every test. And one of its consequences, the ability of massive objects to act as natural telescopes, bending and amplifying light from objects behind them, has become one of the most powerful tools in modern observational astronomy. Clusters like Abell 2744 are not just massive enough to bend light, yet they're massive enough to multiply the apparent brightness of distant objects many times over, in some cases by factors of tens or hundreds. This is the reason James Webb can see objects that, by rights, should be invisible. Not because the telescope itself is powerful enough to detect them directly, but because the universe has helpfully placed enormous gravitational lenses in the line of sight, amplifying the light before it reaches the telescope's mirror. It's as if the cosmos, for reasons that have nothing to do with any intent or design, purely through the operation of ordinary physical laws, has arranged things to make itself legible to any intelligent observer patient enough to figure out where to look and how to interpret what they see. This connects to something the JWST scripts we analyzed earlier pointed to as one of the most philosophically striking aspects of modern cosmology. The universe doesn't seem to have been designed to be observed. It doesn't need observers to exist. The laws of physics operate with perfect indifference to whether anyone is there to note their operation. And yet the same laws that govern the expansion of space and the bending of light and the formation of galaxies also gave rise, after billions of years of patient operation, to creatures capable of building telescopes and using gravitational lensing to see galaxies from before those creatures' home planet existed. There's something in that coincidence, or non-coincidence, that resists being fully absorbed. The universe arranged for its own legibility. Whether that observation carries any deeper meaning is a question that science, by its nature, is not equipped to answer. But the fact of it is remarkable, and sitting with it quietly for a moment feels like the right response. Let's return to the specifics of what James Webb is finding and what it means for our understanding of the universe's first chapter. One of the most important discoveries in the first years of operation involved not just the detection of ancient galaxies, but the measurement of their chemical compositions. As we discussed, finding oxygen in a galaxy from when the universe was only a few 100 million years old was startling. But the oxygen discovery was part of a broader pattern, a consistent finding that the early universe had achieved chemical complexity far faster than the standard model predicts. The way astronomers measure the chemical composition of a distant galaxy is elegant. When light from that galaxy passes through the intergalactic medium and eventually reaches Earth, some of that light has specific wavelengths absorbed or emitted by particular atoms in the galaxy's gas. Each element has a unique spectral fingerprint, a characteristic set of wavelengths it absorbs or emits. By spreading the galaxy's light out into its constituent wavelengths and looking for those fingerprints, astronomers can determine what elements are present and in what quantities. This technique, spectroscopy, is one of the foundational tools of modern astronomy, and it works across essentially all distances because the physical laws governing atomic structure are the same everywhere in the universe. As the challenge with very distant galaxies is that their light has been so redshifted, stretched to longer wavelengths by the expansion of space, that the spectral fingerprints have moved out of visible wavelengths and into the infrared, exactly the regime where James Webb is most sensitive. This is another way in which the telescope was perfectly designed for this science. Its infrared instruments can decode the spectral fingerprints of galaxies from the earliest cosmic epochs in a way that was impossible for any previous observatory. And what those fingerprints have been showing is consistent and troubling. The earliest galaxies contain far more heavy elements, oxygen, carbon, nitrogen, than they should. Not slightly more, significantly more, in some cases 10 times more. And the chemical enrichment that cosmological models predict should have taken billions of years was apparently happening in hundreds of millions. This is not a quirk of a single unusual object. It's showing up across multiple independent data sets from multiple teams using multiple instruments and analysis methods. It's a pattern, and patterns in science don't usually go away when you look at them more carefully. They either deepen or they reveal their origin. This one is deepening. To understand what might explain this chemical precocity, it helps to think about the stellar populations that would have been present in those first galaxies. If the first generation of stars, population 3 stars, formed from pure hydrogen and helium, was genuinely as extreme as some models suggest, and then their supernovae would have been correspondingly extreme. More massive stars produce supernovae of greater energy. More energetic supernovae scatter their heavy elements more widely and more efficiently. A galaxy in which the first generation of stars was composed mainly of these enormous, short-lived, explosively dying giants would have been chemically enriched much faster than a galaxy forming stars similar to those we see today. One generation of massive population 3 stars, living fast and dying young, could have produced more chemical enrichment in a few million years than many generations of more modest stars spread over hundreds of millions of years. This is an area of active and lively debate in astronomy right now. Nobody has directly detected a population 3 star. As they're expected to be so massive that they should have burned out long before we can see them, even with James Webb, but the chemical signatures they should leave behind, particular ratios of elements, specific patterns of abundance, might be detectable in the spectra of early galaxies, and several research teams are currently searching for exactly those signatures. The presence or absence of population 3 stellar chemistry in these early galaxies could tell us an enormous amount about how the first stars in the universe actually behaved. There's another piece of this puzzle that doesn't get talked about enough. It involves not what the early galaxies contain, but what they look like, their physical structure, their shape, the way stars are distributed within them. In the modern universe, galaxies come in a variety of shapes. Yet there are spirals like the Milky Way, with their elegant rotating disk structure and winding arms of star formation. There are ellipticals, rounder, smoother, generally older galaxies that have used up most of their star-forming gas, and now host mainly old, red stars. There are irregular galaxies, chaotically shaped, often the result of gravitational interactions or mergers. There are dwarf galaxies, tiny systems containing only a few 100 million stars, scattered throughout the galaxy clusters. This diversity of shapes reflects billions of years of evolution, merging, disruption, and settling. The very early galaxies that James Webb has been detecting don't look like any of these familiar categories. They're compact, far more compact than galaxies of similar mass in the modern universe. Some of them appear almost featureless, and without the obvious disk structure or spiral arms that would indicate organized rotation. They're more spherical, more concentrated, more centrally dense. This could reflect the conditions under which they formed. High gas densities, rapid star formation, the violent energy of supernova explosions all happening simultaneously in a compact volume. creating conditions quite different from the relatively placid environments in which most modern star formation occurs. Or it could reflect something about the underlying dark matter halos that hosted them, which in the early universe were themselves smaller, denser, and more extreme than the halos hosting galaxies today. The structure of early galaxies is an area where James Webb is providing genuinely new information. Previous telescopes simply couldn't resolve the internal structure of galaxies at these distances. They appeared as single points of light or at best as small, unresolved blobs. James Webb's combination of resolution and infrared sensitivity is for the first time allowing astronomers to see the shapes of galaxies from the first billion years of cosmic history with real clarity. And what they're seeing is not always what the models predict. One particularly striking set of observations involved what are called little red dots, a nickname given to a population of very compact, very red objects that showed up in James Webb's early wide-field surveys. These objects are abundant, far more abundant than expected, and their colors and compactness initially suggested they might be extremely distant, and extremely active galactic nuclei, essentially very bright quasars at extreme distances. But follow-up spectroscopy has revealed a more complicated picture. Some of them do appear to be active galactic nuclei, with rapidly accreting central black holes contributing significantly to their brightness. Others appear to be compact, intensely star-forming galaxies, their red color a result of the dust created by the star formation itself, absorbing the bluer wavelengths and re-radiating them in the infrared. And some appear to be a mixture of both, galaxies with both active star formation and actively feeding central black holes, both processes contributing to the total light output. The abundance of these little red dots is itself a puzzle. The standard model doesn't predict them to be as common as James Webb finds them, that if they're predominantly galaxies with active black holes, then either black holes in the early universe were more common than expected, or they were growing faster than expected, or both. If they're predominantly dust-enshrouded star-forming galaxies, then star formation in the early universe was not only more efficient, but also more dust-rich than expected, which would have implications for how we interpret other observations, because dust at these early times shouldn't have built up very much yet. There are still far more questions than answers about the little red dots, but their existence, their sheer unexpected abundance, is one of the clearest signals that the early universe was doing things on a schedule that our models hadn't anticipated. All of this brings us to a question that is becoming increasingly unavoidable. What? Exactly. Does it mean that the universe seems to have grown up faster than expected? This isn't just an astronomical puzzle. It's a question about the fundamental physics of the early universe. And it connects in ways that are both interesting and slightly disorienting to some of the deepest open questions in physics. The standard model of cosmology, known technically as the lambda CDM model, for lambda, dark energy, plus CDM, cold dark matter, is built on a small number of foundational assumptions. It assumes that dark matter consists of cold, slow-moving particles that interact with ordinary matter only through gravity. It assumes that dark energy is a fixed property of space itself, a constant energy density that causes the expansion of the universe to accelerate. It assumes that the initial conditions of the universe, the tiny quantum fluctuations in density that seeded all subsequent structure, were produced by a period of exponential expansion in the universe's first fractions of a second, a period called inflation. These assumptions, together with the known laws of gravity and particle physics, give a remarkably precise description of how the universe has evolved from the Big Bang to the present day. But the model makes predictions about the early universe, predictions about how quickly structure should form, how efficiently galaxies should build up their stars, how much chemical enrichment should occur in the first few 100 million years. And some of those predictions are not matching what James Webb is seeing, as the discrepancies aren't yet large enough for most cosmologists to say the model is fundamentally broken. But they're large enough and consistent enough and well verified enough that they're commanding serious scientific attention. One class of proposed solutions involves modifying the properties of dark matter. Standard cold dark matter predicts a particular pattern of structure formation, clumps of a certain typical size forming at a certain typical rate, If dark matter has slightly different properties, if it's warm rather than cold, meaning the dark matter particles move faster and suppress the formation of small halos, or if it interacts with itself or with ordinary matter in subtle ways, then the pattern of structure formation in the early universe could be different, more efficient, faster, producing larger and more massive halos at earlier times than cold dark matter predicts. Several alternative dark matter models have been proposed along these lines, and constraining them with observations is an active area of research. James Webb's observations of the early galaxy population are providing some of the most powerful constraints on dark matter properties ever obtained. Another class of solutions involves modifying how we model the baryonic physics, the physics of ordinary matter, star formation, supernovae, and feedback within the dark matter halos. Our simulations of galaxy formation involve many approximations and simplified descriptions of processes that are actually extremely complex. The way gas cools, the way star formation proceeds, and the way supernova energy couples to the surrounding gas. These are all described by simplified prescriptions in cosmological simulations, not from first principles. It's possible that the real physics of early star formation is sufficiently different from what our simulations assume that the simulations are simply failing to capture how quickly the early universe could build up stellar mass. Improving those simulations, making them more realistic, adding more physics, resolving smaller scales, is ongoing work, and several recent improvements in simulation methodology have closed some of the gap between predictions and observations, though not all of it. A smaller number of theorists have proposed more radical solutions, modifications to the underlying cosmological model itself, as perhaps dark energy is not a constant but varies over time, or has different properties in the early universe than it does today. Perhaps inflation did not proceed in the simple way we assume, producing a different pattern of initial density fluctuations than the standard model predicts. Perhaps there are new fundamental interactions or new fields that operated in the early universe and affected structure formation in ways we haven't accounted for. These ideas are speculative, and most cosmologists regard them as premature, given that more conventional explanations haven't been exhausted. But they're on the table, being discussed seriously, because science requires taking anomalous observations seriously, especially when they're inconvenient for established theory. Here's the thing about the current moment in cosmology that's worth pausing to appreciate. This is what science looks like when it's actually working. When a theory is being genuinely tested against new observations that push into territory the theory has never been confronted with before. The James Webb Space Telescope wasn't built to confirm what we already knew. It was built to see further, deeper, more clearly than anything before it, and inevitably, when you do that, you find things you didn't expect. The standard model of cosmology is not a fairy tale that anyone made up to comfort themselves. It is the product of decades of extraordinarily careful work, tested against thousands of observations, refined by generations of brilliant minds. It is the most precisely tested theory in the history of astronomy, and it is now being confronted with observations that it didn't fully predict. That confrontation is healthy, it's productive, it's exactly what scientific progress looks like. The model may be wrong in some details. It may need to be expanded or modified. Or the observations may eventually find explanations within the existing framework that we just haven't thought of yet. Science doesn't know in advance which of these it will be. That's what makes it science. And it's what makes this moment, right now, in the early years of the James Webb Space Telescope's operations, one of the most exciting moments in the history of cosmology. There is one more discovery from beyond the Dark Ages that deserves its own extended discussion. And because it illustrates the strangeness and the power of what James Webb is doing in a way that's both scientifically significant and, if you let it, genuinely moving. It's the story of a star, a single star, that should have been invisible. Individual stars are almost vanishingly small compared to the distances between galaxies. Our Sun, 109 times the diameter of Earth, is just a point of light in the nearest galaxies to us, hundreds of thousands of light years away. The idea of detecting an individual star in a galaxy billions of light years away. from the period of the Dark Ages, seems not just difficult, but essentially inconceivable. The light from a single star, even a massive one, falls off with distance at the same rate as all light, the square of the distance, at the distances we're talking about, and from galaxies that existed in the first billion years of cosmic time. A single star should be utterly, completely, impossibly invisible. And yet, there's a phenomenon that makes the impossible occasionally possible. The same gravitational lensing that allows James Webb to see distant galaxies that would otherwise be too faint to detect can, under the right circumstances, be focused so precisely that it amplifies the light of a single star to detectable levels. This happens when a very massive foreground object is aligned almost perfectly between Earth and the distant star, and the geometry creates what's called a caustic, a line of maximum amplification, where the gravitational lens focuses with extraordinary precision. And if a star happens to be crossing this caustic, moving through it due to the relative motion of everything involved, its light can be briefly amplified by enormous factors. Not 2 times, not 10 times. Potentially tens of thousands of times, or even more. In 2022, the Hubble Space Telescope detected what appeared to be a single star in a galaxy about 12 billion light-years away, during what appeared to be a caustic crossing event. The object was named Earendel, an Old English word meaning rising light. At the time of detection, Earendel was the most distant individual stellar object ever resolved, light from a single star that had been traveling toward us for 12 billion years before being briefly amplified to detectability by a gravitational lens. The discovery was extraordinary. Then James Webb followed up, yet with its greater infrared sensitivity and its superior spectroscopic capability, and the follow-up measurements added crucial detail. The spectrum of Earendel suggested temperatures in the range of 9,000 to 34,000 Kelvin. Hot, massive stars. The cooler end of that range corresponds to a star already among the most massive known in the local universe. The hotter end corresponds to something at the upper boundary of stellar temperatures. If Earendel is truly a single stellar object, or perhaps a closely paired binary system, it represents not just a detection record but a window into individual stellar physics at cosmic distances in ancient times. But then, in 2025, a team at the University of California, Berkeley published a paper questioning the interpretation of Earendel. Their analysis, careful and detailed, suggested that the object might not be a single star at all. It might instead be a compact ancient star cluster, a dense collection of hundreds of thousands of stars packed into a tiny volume, the kind of object that is thought to be the precursor of the ancient globular clusters that orbit mature galaxies today. Their argument rested on the chemical fingerprints in Earendel's spectrum, its apparent size relative to the gravitational magnification, and its similarity to other objects along the same lensed arc that had already been tentatively identified as compact star clusters rather than individual stars. The debate about Earendel's true nature is ongoing. It hasn't been resolved. The magnification estimates carry enough uncertainty to allow for both interpretations, and different features of the data favor different conclusions. And additional observations, not yet scheduled as of early 2026, will likely be needed to settle the question definitively. But here's what's remarkable about the situation. Regardless of which interpretation turns out to be correct, Earendel represents a measurement at a distance and an epoch that would have seemed like science fiction 20 years ago. Whether it's a single massive star or a compact precursor to today's globular clusters, it's an object from the universe's first billion years that we can analyze spectroscopically, that we can measure the temperature of, estimate the chemical composition of, begin to understand as a physical object rather than just a point of light in a deep field image. The frontier of individual stellar detection has been pushed to a place in the universe where the very first stars were forming. And that is genuinely new territory. The story of Earendel connects to a deeper question that cosmology is currently wrestling with. When we talk about the first object beyond the Dark Ages, the thing that the James Webb Space Telescope found that stunned everyone, we're not talking about a single moment of discovery, a single object spotted on a single night. We're talking about a growing catalog, a pattern, a consistency of findings that together paint a picture of an early universe that was more active, more energetic, more chemically complex, and more structurally developed than our models predicted. Arundel might be a single star from that era. MOM-Z14 is a whole galaxy from even earlier. The cosmic gems are 5 dense star clusters from the first 460 million years. The oxygen-rich galaxy is a chemically mature system from when the universe was barely 290 million years old. Together, these discoveries are not just headline-grabbing individual finds. They're telling a coherent, if puzzling, story. The universe grew up faster than we thought. There's a way of thinking about this that I find particularly illuminating. Imagine you're an archaeologist, and you've been excavating a historical site that you believe was established around 500 years ago. Your models of how communities develop, how they go from first settlement to established town, suggest that after 500 years, you should find a modest community, early buildings, simple tools, the first signs of organized agriculture, maybe the beginning of trade networks. Instead, when you dig, you find the remains of a fully developed city, complex architecture, sophisticated metalwork, evidence of long-distance trade, literary texts, bureaucratic records. The city is 500 years old, as dated, but it looks 500 years more developed than it should. Something about the story of how communities develop, the timeline you believed in, was wrong. That's roughly where cosmology is right now with the early universe. The excavation is proceeding beautifully. The dating is reliable. The objects being found are real and well characterized. But the timeline of development they imply doesn't match the standard story. And in the question of what needs to change in that story, what was missing from our understanding of how the early universe developed, is one of the most active areas of scientific investigation on the planet right now. Let's step back from the specifics for a moment and think about what this means on the largest possible scale, not just for our understanding of galaxy formation, but for our understanding of cosmology itself and our place in the story of everything. The universe has a history. It's a history that began 13.8 billion years ago, went through a dark and quiet period during which the raw material of everything future was assembling itself, then burst into light as the first stars ignited, and has been evolving, building complexity, growing structures, seeding gas clouds with heavy elements, forming planets, and creating the conditions for chemistry ever since. We are participants in that history, not spectators. Every atom in your body was forged in the interior of a star that lived and died before our solar system existed. You are made of ancient, stellar ash, reading about the history of the universe that made you. That's not poetry. It's literally true. And now we're finding that the early chapters of that history were more dramatic, more productive, more complex than we realized. The universe was in a hurry to make things, in a hurry to forge the first heavy elements, in a hurry to build the first galaxies and the first dense star clusters and the first chemical conditions that would eventually, billions of years later, allow the emergence of planetary systems and the chemistry of life. Whether this has any implications for questions about how common planets are, how common the conditions for life might be, how widespread the chemistry of biology might be across the cosmos. Those connections are tentative and speculative, but they're not nothing. If the early universe was more productive than expected, if it was forming stars faster, enriching gas with heavy elements sooner, building the foundations for planetary systems earlier, then the window during which complex chemistry and potentially life could exist in the universe is longer than we thought. The first stars, enriching the first gas clouds, seeding the first planetary systems, potentially beginning the very first cycles of complex chemistry. Those might have begun hundreds of millions of years earlier than we assumed. That doesn't mean life is common. Yes, it doesn't mean life is anywhere other than Earth. We have no evidence of life anywhere else, and the Fermi paradox, the silence of the cosmos in response to 65 years of searching, reminds us not to assume abundance. But it does mean that if the conditions for life can arise, they had more time to do so than we thought. Time that was being used in those early galaxies to build the raw materials. Let's talk about how the James Webb Space Telescope actually works, because understanding the instrument helps you understand what it's doing when it peers back into the dark ages. The basic principle of a telescope is simple. Gather as much light as possible and focus it onto a detector. The more light you gather, the fainter the objects you can detect. And the size of the primary mirror, the main light-gathering surface, determines how much light you can collect. James Webb's primary mirror is 6.5 meters in diameter, made of 18 hexagonal gold-coated beryllium segments that fold up for launch and unfold in space. Gold reflects infrared light extremely well. Beryllium is extraordinarily light and stiff, essential for a mirror that has to unfold in space and maintain its precise shape while being cooled to cryogenic temperatures. The telescope sits at a location called L2, the second Lagrange point of the Earth-Sun system, about 1 million miles from Earth in the direction away from the Sun. At this point, the gravitational pulls of the Sun and Earth combine with the centrifugal forces of orbital mechanics to create a stable position where the telescope can orbit the Sun at the same rate Earth does, staying roughly in the same relative position. This is important because it means the Sun, Earth, and Moon are always in roughly the same direction, and James Webb's enormous sun shield, roughly the size of a tennis court, can keep all three of them blocked from the telescope's view simultaneously. That sun shield is crucial. James Webb's infrared detectors need to be cold, extremely cold, to function. Infrared radiation is essentially heat radiation, and if the telescope's own temperature is too high, the thermal emission from the telescope itself would overwhelm the faint infrared signals from distant galaxies. The sun shield keeps the telescope's instruments cooled to about minus 233 degrees Celsius, within 40 degrees of absolute zero. At those temperatures, the thermal noise from the telescope is low enough that the detectors can pick up the incredibly faint infrared light from galaxies that existed hundreds of millions of years after the Big Bang. The detectors themselves are extraordinary pieces of technology. James Webb carries several scientific instruments, each optimized for different kinds of observations. The near-infrared camera, known as NIRCam, is the primary imaging instrument, capable of producing the stunning, wide-field images of thousands of galaxies that have become iconic since the telescope's first light. The near-infrared spectrograph, NIRSpec, can simultaneously take spectra of up to 200 objects in a single pointing, breaking their light into constituent wavelengths and measuring the chemical fingerprints of hundreds of distant galaxies at once, in what would have previously required hundreds of separate observations. The mid-infrared instrument, MIRI, operates at even longer wavelengths, in the mid-infrared range, where the thermal emission from dust-enshrouded galaxies is brightest, and where some of the most ancient galaxies appear most clearly. The fine guidance sensors and near-infrared imager and slitless spectrograph, NIRIS, provides additional imaging and spectroscopic capabilities. Together, these instruments have turned James Webb into a machine for exploring the very edge of cosmic time. And the quality of data it's producing, the signal-to-noise ratios, the spectral resolution, the spatial resolution, have routinely exceeded the most optimistic pre-launch predictions. When scientists describe their surprise at what the telescope has found, they're not just surprised by the objects themselves. They're surprised by how clearly the telescope is seeing them. How much detail it can extract from light that has been traveling for 13 billion years. The telescope didn't just meet its specifications, it exceeded them in ways that have made the science richer than anyone dared hope. One of the most scientifically productive modes of operation for James Webb has been survey work, pointing the telescope at a patch of sky and taking very long, very deep exposures that reveal the faintest possible objects. The Cosmos Webb survey, completed in 2025, and covered an area of sky roughly 3 times the size of the full moon, and detected nearly 800,000 galaxies, each measured in 37 different wavelength bands. That's 800,000 separate galaxies, each a universe of hundreds of billions of stars, each characterized well enough to estimate its distance, its stellar mass, its star formation rate, and its chemical properties. The catalog is an archaeological dig through 13 billion years of cosmic history, every galaxy in it a data point on the timeline of how the universe grew from its early chaos into the structured, complex cosmos we inhabit today. The cosmic dark ages that preceded all of those galaxies are, by definition, invisible in such surveys. The dark ages left no light, no electromagnetic signal of any kind that any telescope could detect. They are visible only in their absence, in the properties of the earliest galaxies that James Webb can see, which bear the imprint of what preceded them. The chemical composition of the first galaxies reflects the conditions of the dark ages, the temperature and density of the gas, the nature of the dark matter halos, the initial conditions of collapse. The structure of the first galaxies reflects the physics of the dark ages, how gas cooled and fragmented, how dark matter halos grew and merged, how the transition from smooth gas cloud to organized stellar system actually proceeded. The first galaxies are not just objects of interest in themselves. They are records of what came before them. They are the first pages of a story that began in a darkness we will never be able to directly observe. And this is one of the things that makes the discovery of objects from beyond the dark ages so scientifically important. Not just because of the objects themselves, as extraordinary as they are, but because those objects encode information about the dark ages that we can read, if we're careful enough and clever enough, from their properties. The chemical abundances in MOM-Z14, or in the oxygen-rich galaxy from 290 million years after the Big Bang, tell us about the stellar populations that preceded them, the first generation of stars, the population 3 objects, whose properties shaped the chemical evolution of the early universe. The structural properties of the cosmic gems clusters tell us about the physical conditions in the first dense star-forming regions, conditions that no longer exist anywhere in the observable universe but that shaped the evolution of everything that followed. The gravitational lensing that makes Arundel visible tells us about the mass distribution in early galaxy clusters, which in turn reflects the nature of the dark matter halos in which those clusters formed. Every one of these objects is a window not just onto itself, but onto a period of cosmic history that is otherwise permanently inaccessible to direct observation. The dark ages can't be photographed. They left no light. But the first objects that formed after those ages carry the memory of what they emerged from. And James Webb is reading that memory with a clarity that was impossible until now. Let's spend some time on a question that has been lurking in the background of everything we've discussed. What does it mean for our models of the early universe that they're being challenged by observations? How should we think about the discrepancy between what the standard model of cosmology predicts and what James Webb has been finding? Science operates on a kind of productive tension. A theory or model is proposed, it makes predictions, those predictions are tested against observations, and the results either confirm the theory or force it to be revised. The history of science is full of theories that looked secure and were then overturned, or more commonly expanded and refined, by observations that pushed into new territory. Newtonian mechanics seemed essentially complete at the end of the 19th century, and then relativity and quantum mechanics revealed that it was an excellent approximation, valid in a specific regime, but breaking down at very high velocities and very small scales. The standard model of particle physics is extraordinary in its precision and predictive power, and yet we know it's incomplete because it doesn't incorporate gravity, and it doesn't explain dark matter or dark energy. In each case, an apparently successful theory revealed its limitations at the edges of the domain it was applied to, and those limitations drove the development of something better and deeper. The standard cosmological model is now being applied to regimes. The very early universe, yet the first few 100 million years after the Big Bang, that it has never been genuinely tested against before. Not because those regimes weren't important, but because, until James Webb, we didn't have the observational capability to probe them with sufficient precision and depth. James Webb is the first instrument that has given us real observational leverage on the era when the first galaxies were forming, and the observations it's producing are revealing discrepancies that suggest our models of early galaxy formation need to be revised, extended, or possibly even replaced with something more complete. Most cosmologists, being cautious and rigorous scientists, are not yet ready to say the standard model is broken. They're saying it's under stress. Yet they're saying that our understanding of the early universe physics of star formation is likely incomplete. They're saying that some combination of more efficient early star formation, different initial stellar populations, modified feedback physics, and possibly modifications to dark matter properties is probably needed to explain the observations. This is the consensus view as of early 2026, and it's a view held by thoughtful scientists who have spent careers studying these questions. But there's also a minority view, taken seriously by serious people, that the discrepancies might point to something more fundamental, a property of the universe's initial conditions or fundamental physics that the standard model doesn't capture. This view remains speculative, and it's the kind of scientific speculation that needs to be held lightly. But it's worth noting that in the history of physics, the minority view has sometimes turned out to be correct. The anomalous precession of Mercury's orbit was a small discrepancy in Newtonian mechanics that seemed like a detail but actually pointed toward general relativity. The ultraviolet catastrophe in classical physics seemed like a minor technical problem that actually required quantum mechanics to resolve. Small discrepancies, persistently present across multiple independent observations, have a history of pointing toward something genuinely new. Whether the James Webb discrepancies are in that category or in the category of phenomena that will be explained within the existing framework, nobody knows yet. That's what makes science at the frontier genuinely exciting. And there's one aspect of the James Webb discoveries that deserves more attention than it typically receives in popular science discussions, and that's the role of the scientific community itself, of the human beings who built this telescope, who designed the observations, who analyzed the data, who argued about interpretations, who published papers and peer-reviewed each other's work, and who are now, collectively, trying to understand what they've found. Science is often presented as a smooth, linear march toward truth. In reality, it's messy, contested, collaborative, and deeply human. And the current moment in cosmology, with all its exciting discoveries and all its unresolved debates, is a vivid illustration of that. When a new observation challenges an established theory, and the first response of the scientific community is generally skepticism. Not hostility, but appropriate caution. The first step is to ask whether the observation itself is reliable, whether the distance estimates are correct, whether the measurements are well calibrated, whether systematic errors have been accounted for. In the case of James Webb's early galaxy findings, this process has been going on since the first results were published. Some early distance records, announced with considerable excitement, have been revised downward after more careful spectroscopic follow-up. Objects that seemed extraordinarily distant based on photometric estimates turned out, when measured more precisely, to be at lower redshifts, not because the telescope was making errors, but because the photometric redshift technique, while powerful, has known failure modes that careful spectroscopy can correct. This revision process is not a failure of science. It's science working exactly as it should. Preliminary results get refined, strong claims get scrutinized. The ones that survive scrutiny are the ones that represent real knowledge. And many of James Webb's most striking results have survived that scrutiny. MOM-Z14's redshift was confirmed spectroscopically. Not just estimated from imaging colors, but measured directly from the wavelengths of specific atomic emission lines. The oxygen discovery was independently confirmed by two separate teams. The cosmic GEMS clusters have been studied in multiple independent analyses that all point to the same basic picture. These are not preliminary claims that might evaporate under scrutiny. Yet they're findings that have already been scrutinized and held up. The scientific community's caution has been applied, and the results are still there. This is an important point to emphasize, because in popular science communication, there's sometimes a tendency to either breathlessly oversell preliminary findings as revolutionary discoveries, or to dismiss all claims of anomalous results as probably going to be explained away. Neither extreme is accurate. The truth is that James Webb is producing a growing body of well-verified results that are creating real tension with the predictions of the standard cosmological model. The tension is real. The observations are real. What remains uncertain is what the tension means. What physical explanation will ultimately resolve it? But the discrepancy itself, and between what the models predicted and what the observations show, is not going away. It's deepening as more data comes in, and it's deepening in ways that are pointing toward a consistent conclusion. The universe in its earliest days, in the period just emerging from the cosmic dark ages, was more energetically productive, more chemically active, more structurally developed, and in some ways more mature than any previous theory had suggested. Whatever was happening in those first few 100 million years was remarkable. And we are only now, with the James Webb Space Telescope and the extraordinary community of scientists studying its data, beginning to understand what it was. There's something that hasn't been mentioned yet that deserves to be brought in here. Yeah, because it connects the cosmic story we've been telling to something that might feel more personal. The heavy elements forged in the first generation of stars, the oxygen and carbon and iron scattered into space by the first supernovae, inherited by the next generation of stars and their planetary systems. Those elements eventually found their way, through billions of years of cosmic recycling and stellar generations, into the gas cloud that collapsed to form our sun and our solar system 4.5 billion years ago. The oxygen in Earth's atmosphere, the carbon in the DNA of every living thing, the iron in your blood, all of it traces back through multiple generations of stellar evolution to that first generation of stars that formed in the first few 100 million years of cosmic time. The stars we're studying with James Webb are not just interesting objects in the early universe. They're, in a very literal chemical sense, our ancestors. We are made of what they made. When astronomers measure the oxygen abundance in a galaxy from 290 million years after the Big Bang and find it surprisingly high, they're not just collecting a data point about distant physics. They're reading an entry in a chemical genealogy that ultimately includes us. The chemical enrichment that those ancient galaxies were performing, faster and more efficiently than expected, was the beginning of the long chain of stellar generations that would eventually produce, among other things, the atoms in the bodies of the people who built the telescope that's measuring them. There's something quietly extraordinary about that closed loop. The universe is studying itself, using tools made of materials it made in its own past, looking back at the moment when those materials were first being made. This is not a comfortable or simple idea. It requires holding together, simultaneously, the vastness of cosmic time and space, and the smallness and contingency of human existence. It requires accepting that we are both utterly insignificant. One species on one planet orbiting one ordinary star in one typical galaxy among 2 trillion, and also, by any measure, extraordinary. The only thing in the observable universe, as far as we know, that looks back at all of this and tries to understand it. Whether those two facts can be reconciled, whether they point toward anything beyond themselves, is not a question that science can answer. But the facts themselves are real. And sitting with both of them simultaneously, without collapsing into either self-aggrandizement or nihilism, might be the most genuinely philosophical response to what James Webb has been showing us. Let's now go deeper into some of the specific technical discoveries that have come out of the James Webb observations of the early universe, because they deserve more than a surface treatment. Some of them are technically intricate, but the underlying ideas are accessible, and the details matter. One of the most powerful techniques James Webb has deployed in studying early galaxies is what's called dropout selection. When a galaxy is at a high redshift, when it's very far away and we're seeing it at an early cosmic time, the light it emitted has been redshifted significantly. One particularly useful signature is the Lyman break. Hydrogen gas, and there's a lot of hydrogen in and around every galaxy, is extremely efficient at absorbing ultraviolet photons below a specific wavelength, specifically photons with energies above the ionization energy of hydrogen. Any light emitted by a galaxy at wavelengths shorter than this limit gets absorbed before it can escape the galaxy. The result is that distant galaxies have a sharp cutoff in their spectrum. They're bright at wavelengths longer than the redshifted Lyman limit, and they essentially disappear at wavelengths shorter than it. Now, this creates a distinctive signature. A galaxy that's detected in some wavelength bands but completely absent in others. It drops out of the shorter wavelength images. By looking at which band a galaxy drops out of, you can estimate its redshift and therefore its distance. This technique, called dropout selection, or photometric redshift estimation, has been used for decades with optical telescopes to find moderately distant galaxies. James Webb applies it in the infrared, which allows it to find much more distant galaxies, ones where the Lyman break has been redshifted all the way into the infrared. The Lyman break dropout technique is a screening tool. It identifies candidates for very distant galaxies based on their colors and their presence or absence in different imaging bands, but it's only a first step. And the distances it provides are estimates, not measurements. To get a real distance, a confirmed reliable redshift, you need spectroscopy. And James Webb's spectroscopic instruments, particularly NIR spec, have been making the confirmations. The process is painstaking but powerful. Image a wide field, identify dropout candidates, point the spectrograph at the candidates, measure their actual spectral features, confirm or revise the redshift estimates. This has been the workflow that has produced the catalog of confirmed high redshift galaxies from the early universe. The confirmed discoveries, the ones that have made it through spectroscopic verification, are the bedrock of what we know about the early universe. MOM-Z14 at a redshift of 14, corresponding to 280 million years after the Big Bang, now has a spectroscopically confirmed distance. The oxygen-rich galaxy at a redshift of about 13, corresponding to about 290 million years, has a spectroscopically confirmed distance and a spectroscopically measured chemical composition. The cosmic GEMS arc at a redshift of about 10 has a spectroscopically confirmed distance and spectroscopically measured properties of the star clusters within it. These findings are not going to be revised away. They're real. And collectively, they paint a picture of the universe in its first 500 million years that is remarkably different from what the standard model predicted. A universe that was already building massive, chemically complex structures when it was only 2 to 3% of its current age, and a universe where the first generation of stars was apparently so efficient at forming and so energetic in their deaths that they rapidly enriched the surrounding gas with heavy elements. A universe where the first dense star clusters were forming with properties, stellar densities, stellar mass functions that are quite different from anything we see forming in the modern universe, and that may have been the birthplaces of some of the most exotic objects, intermediate mass black holes, for instance, whose origins have been debated for years. The picture is incomplete. We're seeing only the brightest, most extreme objects from this era, the ones luminous enough or sufficiently amplified by gravitational lensing to be detected across such enormous distances. The typical early galaxy, if there is such a thing, is probably fainter and harder to see. The objects we're finding are likely among the most energetically productive of their time, not a representative sample of all galaxies from the early universe. This selection effect is important to remember. The sample we have is the tail of a distribution, the brightest end. The average is unknown, and what the average looks like might be quite different from the extreme objects that are currently dominating the headlines. But even knowing that the current sample is biased toward the extremes doesn't resolve the fundamental tension. Because even if the average early galaxy was much less extreme than MOM-Z14 or the oxygen-rich galaxy, the very existence of those extreme objects at those early times constrains what the early universe was capable of. Well, if the universe produced even one galaxy as massive and chemically complex as the most extreme objects James Webb has found at a redshift of 13 or 14, then the early universe was capable of doing things that the standard model says it shouldn't have been capable of yet. A model that can't produce even the most extreme outlier, under any conditions, is a model that needs to be revised. And the standard model, in its current form, struggles to produce those extreme outliers. The gap between the model's predictions and the observations is real, statistically significant, and present across multiple independent datasets and multiple independent analysis groups. The scientific community is taking it seriously. And the search for the physical explanation, the mechanism that would allow the early universe to be this productive, is one of the most active and exciting areas of research in modern astrophysics. Let's now turn to a question that underlies all of this, a question that's been implicit in everything we've discussed, but that deserves to be stated explicitly. What does it mean to see the beginning? What are we actually doing when we point a telescope at something 13.5 billion light years away and call what we see the early universe? Light travels at a finite speed. When you look at a distant object, you see it not as it is now, but as it was when the light left it. Look at the moon, and you see it as it was about 1.25 seconds ago, essentially now, on any practical timescale. Look at the sun, and you see it as it was about 8 minutes ago. Look at the nearest star beyond the sun, Proxima Centauri, and you see it as it was about 4 years ago. Look at the Andromeda Galaxy, the nearest large galaxy to our own, and you see it as it was 2.5 million years ago, when our ancestors were still making stone tools on the African plains. That ancient light has been crossing space ever since, long before we existed to receive it, and it arrives at our telescopes carrying the image of something that no longer looks quite the same as when that light departed. Now push that to the extreme. When James Webb detects the light from MOM-Z14, a galaxy whose light traveled for 13.5 billion years, it's seeing that galaxy as it was 13.5 billion years ago. At a point when the universe was only 280 million years old, when the atoms in your body hadn't been forged yet, when our solar system was nothing more than a region of interstellar gas that happened eventually, after billions of years of further evolution, to be in the right place to collapse and form a sun and its planets. When the very oxygen you're breathing right now was still locked in the core of a star that hadn't even been born yet. Every deep field image from James Webb is, in this sense, an archaeological dig through time. The light from nearby galaxies departed relatively recently. The light from intermediate distance galaxies departed billions of years ago. The light from the most distant objects in any given image departed when the universe was just beginning. All of that light, and from all of those cosmic epochs, is arriving simultaneously and being decoded into a single image. Looking at a James Webb deep field is looking at all of cosmic history, compressed and flattened into a single plane of light. It's a core drilled through time, different layers representing different eras, the way rings in a tree trunk represent different years, or the way sediment layers in rock represent different geological periods. The telescope is a time machine. But it's a one-way time machine that shows you only the past, and only as it appeared when the light you're collecting departed. The galaxies James Webb is studying in the earliest epochs no longer look the way they look in the images. In the 13.5 billion years since that light left them, those galaxies have evolved. They've merged with other galaxies. Yet they've formed new stars and watched old ones die. They've been stripped of gas by the gravitational interactions of the growing cosmic web. Some of them have grown into massive elliptical galaxies that now anchor large galaxy clusters. Some of them have been absorbed into larger galaxies. The early universe that James Webb is photographing is a real place that really existed, but it no longer exists. It's gone, replaced by the universe we live in today. The images we're making of it are the only record it left. This is one of the things that makes the cosmic Dark Ages such a philosophically interesting period. The Dark Ages left no record at all. No light from them survives. We can only infer what happened during that period, what the gas was doing, how the dark matter halos were growing, and how the conditions for the first stars were assembling. From the properties of the objects that emerged from it. The first light, the epoch of Ryanization, the first stars, the first galaxies, is the earliest record we have of the universe's history after the cosmic microwave background. And what that record is showing us through the James Webb Space Telescope is more complex and surprising than we anticipated. Consider what it means that the James Webb Space Telescope exists and is functioning. It took 30 years to go from initial concept to launch. Thousands of scientists and engineers contributed to its development. It was built in pieces by institutions in multiple countries, assembled with tolerances measured in nanometers, tested in conditions designed to mimic the cold of space, folded up for launch, and deployed in a sequence of operations so complex that a single failure anywhere in the process could have been catastrophic, and finally settled at its destination 1 million miles from Earth, unfolding its golden mirror and its sun shield, cooling its instruments to within a whisper of absolute zero, and beginning to collect light that has been traveling since before our planet existed. All of that, the decades of work, the cooperation, the billions of dollars of investment, the incredible precision of the engineering, was done because a species, on a small planet orbiting an ordinary star, decided that understanding the universe was worth the effort, not because it would produce immediate practical benefits, not because there was a clear return on investment in any conventional sense, but because really looking at the cosmos is something that our species does when it's operating at its best. Because the questions the telescope is designed to answer: when did the first stars form? How did the first galaxies build up? What happened in the cosmic dark ages? Are the most fundamental questions we can ask about the nature of the universe we inhabit. And the answers it's finding, strange and puzzling and not entirely fitting our expectations, are doing what good science always does. They're telling us that the universe is more interesting than we thought, more complex, more surprising, more resistant to our desire for simple, clean stories. The cosmic dark ages gave way not to the gradual, orderly emergence of simple structures that our models predicted, but to something more energetic, more productive, more chemically ambitious. The universe was in a hurry to make things, and we are only now beginning to understand why. Here's something worth sitting with before we draw toward a close. The fact that we find these early discoveries puzzling is itself a sign of progress. 100 years ago, we didn't know galaxies existed beyond our own Milky Way. Edwin Hubble's discovery in the 1920s that the fuzzy patches called spiral nebulae were actually separate, distant galaxies was a revolutionary expansion of our cosmic horizon. 50 years ago, we had only the roughest idea of the history of the universe. We knew it was expanding, but the detailed timeline of cosmic evolution was only beginning to be worked out. 30 years ago, we discovered that the expansion of the universe is accelerating, and driven by something we still call dark energy because we have no better name for whatever it is. Every time we've pushed deeper, with bigger telescopes, better instruments, more sophisticated analysis, we've found a universe richer and more complex than what was visible before. The James Webb Space Telescope is the latest step in that long chain of expansion. And like every previous step, it's bringing us closer to the truth, while simultaneously revealing how much we still don't understand. The early universe is not a solved problem. It's a problem we're now, for the first time, actually able to attack with real observational data. The discrepancies between our models and James Webb's observations are not failures. They're the universe's way of telling us where the interesting physics is. If they're signposts toward the things we're missing, the physical processes we've modeled incorrectly, the assumptions we've been making that don't quite match reality. And at the center of all of this, at the heart of what it means that James Webb looked beyond the dark ages and found something that stunned everyone, is a simple but profound truth about the nature of knowledge. We know more than we did before. And knowing more, we know better how much we don't know. The frontier has moved, the mystery has deepened, and the instruments that can probe that deeper mystery are, right now, floating in deep space, collecting light that has been traveling since the universe was young, and sending it back to the planet where the wondering creatures who built them are waiting to see what comes next. But the cosmic dark ages ended with fire, with the ignition of the first stars, with the beginning of the epoch of ionization, with the universe's transition from cold and dark and quiet to luminous and complex and filled with the activity of stellar birth and death. That transition was one of the most important events in the history of the universe, and we are only now, with the tools we've built in just the last few decades, beginning to understand what it actually looked like, how quickly it happened, and what it produced. What it produced in those first hundreds of millions of years was more dramatic and more surprising than we expected. Galaxies more massive than they should have been. Stars more numerous than the models predicted. Chemical enrichment faster than any prior generation of astronomers thought possible. dense clusters of stars that may have been the birthplaces of exotic objects we've been searching for in the nearby universe, and individual stellar objects, or stellar systems, detectable at distances that should have been completely beyond reach, made visible only by the chance alignment of a gravitational lens, with a star crossing its line of maximum amplification. All of this, every discovery from beyond the Dark Ages, is telling us the same fundamental thing. The universe had more going on in its early pages than we wrote into our models. It was a more dramatic, more energetically productive, more chemically ambitious entity in its youth than we gave it credit for. And while that creates real challenges for our theoretical framework, it also makes the story richer, more interesting, more worth telling and retelling as we gradually figure out what it means. The James Webb Space Telescope is not done. It's designed to operate for at least 10 years, and it may last considerably longer if its systems remain healthy and its fuel supply, used for course corrections and orbit maintenance, holds out. In the remaining years of its operation, it will survey more of the early universe. It will find more galaxies from the first few 100 million years of cosmic time. It will measure their properties with greater precision and greater spectral coverage. It will probe deeper into the cosmic dark ages, finding objects from earlier and earlier times, pushing the limits of what it means to look back at the beginning. And at every step it will be comparing what it finds to what the models predict, and in either confirming those models or compelling them to be revised. The scientific community studying its data is engaged in one of the most profound investigations in the history of human knowledge. They are trying to understand the beginning, not the very beginning, the first fraction of a second, the moment of the Big Bang itself, which is beyond the reach of any telescope, but the beginning in the sense that matters most to the story of everything that followed. The first stars, the first galaxies, the first heavy elements, the first chemical complexity. The moment when the universe went from being a cold, dark sea of gas to being a place where interesting things could happen. A place where, eventually, the interesting things that happened would include the emergence of beings capable of wondering about their origins. Yeah, we are those beings. And we are, right now, in the early years of the 21st century, building the tools and developing the techniques to actually answer those questions. Not perfectly, not completely, but genuinely. The James Webb Space Telescope is showing us the universe as it was when it was young. And what it's showing us is strange and beautiful and puzzling in all the right ways. It's a universe that was in a hurry to grow up, that built complexity faster than our models expected, that left behind relics in the form of ancient, dense star clusters and chemically mature galaxies that we're only now beginning to read with sufficient clarity to understand. The cosmic dark ages were the last time the universe was simple. After the dark ages ended, after the first stars lit up, after the epoch of ionization transformed the cosmic gas from neutral and opaque back to ionized and transparent, after the first galaxies formed and grew and merged and evolved, the universe has been getting progressively more complex, progressively more structured, progressively more interesting ever since. We are the current products of that increasing complexity, made of star-forged atoms, living on a rocky planet built from the debris of ancient stellar explosions, looking up with eyes that evolved over millions of years on that planet and asking where it all came from. And the answer we're getting, from the golden mirrored machine floating 1,000,000 miles away, collecting ancient light and sending it home for us to decode, is that it started faster, bigger, and stranger than we thought. The beginning was not the calm, gradual, orderly affair the standard model suggested. It was more dramatic, more productive, more mysterious. And the deeper we look, the more mysterious it becomes. That's how it should be. That's what good science feels like. Not the comfortable confirmation of what we already believed, but the discovery that reality is stranger and richer than the models we built to describe it. The cosmic dark ages keep their secrets well. But every galaxy James Webb finds from just beyond their edge is a fragment of the record those dark centuries left behind. And reading those fragments, slowly, carefully, with the best instruments and the sharpest minds our civilization has produced, is one of the most genuinely magnificent things that human beings have ever attempted. And the question of what the James Webb Space Telescope found beyond the dark ages, what stunned everyone, what's shaking the standard model, what's being urgently debated in seminars and conference rooms and the pages of the most prestigious scientific journals on Earth, that question doesn't have a single, simple answer. It has a growing catalog of answers, each one more surprising than the last, each one adding a new dimension to a picture that is becoming simultaneously more detailed and more mysterious. What it found was this: the universe in its earliest days was more extraordinary than we gave it credit for. It was building things when it should have been resting. It was forging heavy elements when the standard timeline said there hadn't been time yet. It was assembling massive structures in what should have been a period of slow and cautious beginnings. It was, in ways we're still working to understand, in a hurry to become the complex, structured, luminous cosmos it would eventually become. And now we're the inheritors of all that ancient urgency. The atoms in your body were forged in those early stars. The carbon and oxygen and iron that make you possible trace their origin back to those first galaxies, forming in the first few 100 million years of cosmic time. You are, in a direct chemical sense, a product of those ancient stellar generations. And the fact that you exist, with a mind capable of understanding that connection, and with the tools to reach across 13.5 billion light years to see where it all began, that, too, is something the universe arranged, through the operation of its own physical laws over the full span of cosmic time. It is worth, at the end of all of this, pausing to let that land, not rushing past it into the next fact or the next discovery, just sitting for a moment with the knowledge that we live in a universe that began in darkness, built its first light in a hurry that surpassed all expectations, spent billions of years growing in complexity and structure, and eventually produced creatures capable of looking back at the darkness where it all began and asking, with genuine scientific rigor and genuine wonder, what happened there? The James Webb Space Telescope is looking, and what it's finding is extraordinary. And the story is only beginning. The cosmic dark ages ended with the first light. We're only now beginning to read what that first light was trying to tell us. And if the first few years of the James Webb Space Telescope's discoveries are any indication, the story that light is telling is wilder, more complex, and more beautiful than anyone dared to predict. We are listening, and the universe, patient and vast and full of ancient light, is speaking.